Welcome to Chapter 2, Limits and Continuity. In class today we talked about calculating average and instantaneous speed. And so we'll start this video actually on the second page of the text and try to understand a little bit more what the definition of a limit really means. If I jog your memory, we used the example of speed in class to motivate why we talk about limits. In particular, we talked about this notation as maybe a solution to the problem that we were having, trying to calculate instant speed. But before we go back to the instant speed example, there are actually a lot of limits that have nothing to do with time or speed. And the goal in this video is to understand more precisely what a limit is and to be able to evaluate them. And basically, this is your AP level question. This is what we're working towards at this moment. What you should remember from class is that f of x, the output or the dependent variable, is the subject of this limit. So we take a limit of a function. And when we say that the limit equals L, the answer to the limit is like a y value from your graph. Now, looking at this limit, we're basically saying as x gets closer to some value a, which is going to be some x value, what happens to the output of the function? In this sense, the limit's doing the same thinking that you do every time you look at a graph. You find your x value and you go up and you look at your y value. Well, if that's all there is to it, it seems silly that we have a whole chapter on it and a whole notation for it, because that's a pretty simple idea. Well, as you may have guessed, it doesn't stay that simple. Although, hold on to that meaning, because that's going to help you. This messy thing is the formal definition of a limit. It's extraordinarily important in college-level calculus, but we're not going to go too deeply into it now. We'll play around with it in class a little bit. You should pause the video here and copy this down into your notes so that I can talk about it tomorrow, but I won't give you time to write it when I do talk about it. Let me simplify the definition just for now. These are three pictures. Now, when we looked at a limit a minute ago, basically we said the limit is just the y value. These three pictures should just convince you that saying the y value is not always a simple thing. For example, I could take the limit at 1 of each of these functions. And although the functions look really similar at this one point, they're all dramatically different. This first function at 1, if I tried to evaluate f of x, I would get undefined. There is no value for y if x equals 1. The second function is different. At x equals 1, the y value is 1. But in both of these graphs, on either side of 1, the y value is looking like it's close to 2. And that's actually what the limit is. It's like, what does it look like it's getting close to, even if at that point it doesn't match up? Now, that doesn't mean we can't take the limit of a normal point. This last graph is just a regular old linear graph. And the limit of this one is also 2, even though the value is perfectly well defined. Don't forget the simple examples. So there are two basic limit rules that are going to determine all of the simplifying we do for the rest of this video and actually the rest of this unit. These are the two rules, and the rules you need to know the names of. The first one is the rule called the limit of a constant. The second is the limit of the identity. Basically, what we see is that if you take a limit of some number k, in this example k has to be a number, the answer of this limit is just the same number k. Conversely, if we take the limit of the identity function, again, f of x equals x is the identity function, and we take the limit of x as it gets close to some number a, the answer is going to be a itself. Let me make this real for you by showing you a couple examples. Okay, so let's look at an example. In this first one, this is the limit as x approaches 3 of 7, and the meaning of this limit is saying what happens to 7 as x gets close to 3. Well, 7 doesn't depend on 3. 7's just 7. Nothing happens to 7. The limit as x approaches 3 of 7 is 7, and that's the limit of a constant. 7 is k, and that's the answer. This second one is the limit as x approaches 3 of x. What this limit is saying is, well, what happens to x as x gets close to 3? And it should be pretty obvious that x gets close to 3 as x gets close to 3. This second one is the limit of the identity. X is the identity function, a is 3. As x gets close to 3, the answer is the same thing as the a value. Here are the ones that you should have just done off to the side, and I'll work them out really quickly before we move on. The first one, the limit as x approaches 0 of 2. This is the limit of a constant. The answer equals the constant. The second one is the limit as x approaches 7 of x. This is the limit of the identity, because that's the identity function. And so the answer is the a value. As x gets close to 7, x gets close to 7. Sounds kind of stupid, I guess. Here's the last one, because we love irrational numbers. The limit as x approaches pi of e. E is a constant. It's just a number. It looks like a variable. It's not. It's a number, which means the limit of a constant is the constant itself. Cool, let's move on. So from these two really simple rules, we can come up with a whole host of properties. And the word theorem is a word we're going to use a million times here. A theorem is something that is true and that you don't have to explain. Theorems are the ultimate reasons. Now, when we introduce them for the first time, we explain why they're true. And after that, you get to call on those theorems for any problems that you're trying to solve. And once you can name the theorem that makes your answer true, you don't have to do any more work. Pause the video here to copy these down. I know it's a lot of writing. It's essential that you learn to understand what these words mean, and we'll be using each of these in examples when you hit play. Now that you have these examples down, let me give you a couple numerical examples that'll make those properties come to life a little bit better. So up here at the top, according to the two limits that we know so far, I know how to take the limit of x and I know how to take the limit of 7, but I wouldn't have known what to do with them together. The properties of limits rule, the sum rule, which you can see peeking up right at the top there, says that this limit has to be the same thing as the limit of x as x approaches 3 plus the limit of 7 as x approaches 3. And the reason that's good news is because I can easily evaluate these limits. This first one is the limit of the identity, which means the answer is a, or 3. This second one is the limit of a constant. So that means that the limit as x approaches 3 of x plus 7 is 10. Now, if you're thinking in your head, this is stupid, why are we using limits? Good thought, hold it, because I trust there's another reason coming. The second way I could test you on these properties would be, instead of just with numerical examples, with an example where you don't really know what the functions are. So there's some function f of x that has a limit of 6 at 2. And there's some other function g whose limit at 2 is 2. I could ask you, well, okay, knowing that, what is the limit as x approaches 2 of f of x divided by g of x? And the quotient property tells us that this has to be the same thing as the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. And again, the reason that's really good news is because this was not something I knew the answer to, but I know the answers to these two individually. And so now I can just substitute the answers in, and I can find out that my final limit is going to be 3. We are playing around with symbols here. Let me give you 2 to try for you, and then we'll move on to some more worthy examples. So the 2 that you tried off to the side look like this. If you got them right, cool, sit tight. If you didn't, listen to the explanation really quickly, because this is where we're going to start in class tomorrow. The limit as x approaches 6 of 2x is the same thing by the product rule as the limit of 2 as x approaches 6 times the limit of x. The product rule says if you have multiplication inside of your limit, you can split it into two limits. Now, this is the limit of a constant, so the answer is 2, and this is the limit of the identity, so the answer is 6, which means 12 is my final answer. For the second one, this is a difference rule. I know that if I have a difference of two defined limits, I can split them apart. So this becomes the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x, which just means 10 minus 3 equals 7. And of course, that last question pointed out that if these two limits had been given were at different a values, then none of this would have been possible. Okay, at this point, you're probably saying, this is ridiculous. We're just evaluating numbers. Well, that's brilliant. If you recognize that basically we're just plugging things in, you're ready to move on. Example 3 in your textbook shows you a little bit more what we really want by studying these properties. When we solve these, I have no doubt that you can pretty quickly figure out that we're going to be able to break everything apart. What I expect is that you understand the reasons why, because eventually I'm going to ask you questions about limits that don't involve easy, familiar functions. So I could ask you, for example, about a limit at some number c. And in this case, we don't know what the number c is, but we could create an expression. So this is what it would look like. For a, we would take that expression and we would apply the sum and difference formulas. And then we would take this expression and we would apply the product and constant multiple rules, which basically say that we can break each of these apart until this is c times c times c, and this is c times 4, and this is just 3. And we get this very simple expression in the end. Again, I'm evaluating a limit even though I don't know a specific number. Similarly, for the second one, we can do the exact same thing. We can break the limit into two limits using the quotient rule. We can break each of the tops and the bottoms into limits and apply the constant property and the identity property to get this simple expression. All of which is seeming like a lot of work for something that's very obvious. Well, it's good that it's obvious to you because it's becoming a theorem. And theorem number 2 says, for polynomial and rational functions, if you have any real number c, then the limit as x approaches c of that function is the same thing as just plugging in c to the function. And there's a special reason for this that's related to the graph that you might start to imagine. But for now, copy it down and let's just use this for what it's worth. It's basically saying that we're going to save ourselves a lot of time. Example 4 from the textbook shows you how we might use this theorem. And I just want to remind you that this theorem only works for polynomials, so you should be able to articulate what a polynomial is. Now, I know that this is a polynomial, which means that evaluating this limit, all I really need to do is plug in 3. And that's true for the first two. C is slightly different because I could plug in fact, this is a rational function, but theorem 2 isn't just for any rational function. Theorem 2 says you can plug in the value down here as long as the function is defined. And in this case, if I were to plug in 2 to the bottom of this function, I would not get a defined value. So at first glance, I can't use theorem 2 to evaluate this limit. But based on today's in-class exercise, I think you'll see that x squared minus 6x plus 8 is the same thing as x minus 2 times x minus 4. And again, I'm just rewriting this function. I haven't changed its value at all. But based on how I rewrote that function, I know that this function is the same thing as just x minus 4 by itself. That's just simple algebra. And now that I have simplified it,